Hello and welcome to another one of Dee's ADD videos. Today we're going to be discussing free body diagrams. Free body diagrams allow you to simplify a complex problem by drawing the essential parts and trying to develop a plan of attack. I'm going to just illustrate a few free body diagrams and hopefully you will get the picture from that. So, if I were to draw a picture of a person pushing a box, a rather large box it looks like. There's the person. What forces are present? Well, we know that there's going to be the force that the person pushes with, right? And that's that direction. And this would be the box. And then there is the weight of the box. This is just for the, we're neglecting the person. We're not looking at the person itself. So, what's that one there? And then the weight of the box, which is mass times gravity. And then because the box is in contact with the surface, there's also a normal force perpendicular to the contact. And I'm going to take the FP out of the box. You gotta think out of the box, people. Okay. So you can develop a axes based off of this. Those are arbitrary in your setting. Try to have them align with the direction of motion for the X, for instance, if the motion's in the X, or Y, if the motion's in the Y, or at whatever angle we're going at. What do I mean by an angle? Let's look at this scenario. Let's say we're pulling a box up a hill. And it's got some angle here, we'll call it theta. And it's being pulled up that direction with some force, right? So this is a rope, so that force would be what? Tension. So what forces do we have present in this box? Well, let's see. What you want to do with this is you want to align the motion in the positive X direction. So we will say the tension right here, when we draw our axes, would be in the positive X direction. Then there is a contact with a surface, right? So there's a normal force exerted straight up. Then there's a weight going straight down. Whatever the mass of the box times gravity is would be the weight. Alright? Now if this box was moving up a frictionless surface, there would be no friction. But if not, we would have one, I'll draw it in blue because it's opposing the natural motion. I don't know if you can hear my puppy in the background howling. I just got 2 new puppies. Again, these are rough draft videos, if you will, so I can do that. So it's kinetic friction moving opposite the direction of motion. So that would be your free body diagram. Now, quick thing to note. I'm going to redraw the forces. There was your normal force. There was the tension. There's a frictional force. and then we have the weight going down. So I'm going to draw my axes in orange, I guess. So this would be my y-axis, perpendicular or parallel with the normal force. And then the x-axis would be along these two, and that way we minimize the number of component vectors we have to find, right? Because there's only one force now, being this weight, that has components that we need to find. So how do we find those components? Well, I'm going to refresh your mind on some geometry that you probably long since have forgotten in order to figure out what this angle right here is. I'm going to show you that that angle is actually the same thing as this angle right here. How do you say? Well, let's see. If you were to look at this angle theta here, and we already said that the axis is in this direction, right? Not too a straight line for an axis, but you get the idea. And we know that we have a x-axis like this. So there's my coordinate system. Well, I had another vector, the weight vector, that was going straight down, right? And what I told you was this angle is the same thing as this angle right here. Well, how do we do that? Let's draw a parallel line. Use your imagination. These are supposed to be parallel. Okay. What we have now allowed us to do is look at a perpendicular bisector here, and that's supposed to be parallel to this line. These two are supposed to be parallel, sorry. So this also would be perpendicular bisector, and then the alternate interior angles then must be congruent. And so therefore this theta and this theta is the same. What do you need to know from that? Just know that the angle of inclination, right, this is an angle of inclination, will always be the same thing as the angle between your weight vector, which is straight down always, and the negative y-axis that you create. Right? So always inclination, that one there. Okay. So that would be a free body diagram. I didn't label the forces. Let me relabel these forces. Kinetic friction, opposing motion created by the tension, the normal force going up, and this would be the weight going down. Okay. All right, let's look at one final example. How about we do something hanging? What forces do we have there? So let's say we have something very heavy that apparently needs a lot of support hanging right there. Okay. Well, what are the forces acting here? Well, and where do we need to look? Well, we would need to know that different angles, right? There's going to be one angle here, there's going to be an angle there, and I'll try to make this one overlying the main axis, same thing with this one. So that would be purely in the x, negative x, and that one would be purely in the positive y. But if this was theta 1 and this is theta 2, all these things would exhibit a tension, and at this junction point we know that the sum of the tensions is equal to 0. You can watch the tension video later on. But what you will be doing is a free body diagram. So at that junction point, we know that we're going to have, we'll call this T1, T2 right there, T3, T4. So at the junction point, we would have T1 or T3 straight up. We would have whatever this mass would elicit a weight, right? And then we'd have the T4 going there, which T4 would have needed to be broken down into components, right? Using this theta 2 that I found. So meaning you would do your trigonometry to figure out what the T4x is, T4y. T3 is purely in the y, and then, oops, wrong direction. We gotta go this way now. Components are usually dashed lines. So here we can find what T2 is using this theta, and then T1 is purely in the negative x direction, and that would be your free body diagram. So I'll weight this first down, and then we have T1 right there. Alright, so again you would do the sum of the forces in the x and the sum of the forces in the y. But that's not what this is about. We'll do an example video later on for that. But those are a couple examples of a free body diagram, or actually a few examples. Make sure you detail, take your time, because aligning the axes in the proper direction will save you a lot of work. You know, taking this for granted that the inclination always equals the angle between the negative weight, right, or the weight in the negative y direction and the negative y-axis. Practice, practice, practice. This should be the first thing you do when you do a physics problem, is draw the free body diagram. So make sure you check out the example videos to further clarify any confusion you might have. Thank you, and have a nice day.